Okay, real talk. You've seen the sky literally every single day of your entire life, and if someone asked you right now, "Hey, why is it blue?" you'd probably say something like, because it reflects the ocean," or something about the atmosphere. And look, I don't blame you, because here's the wild part. The answer you probably learned in school, if you learned anything at all, is incomplete. It's not wrong, exactly, but it's missing the most fascinating pieces of the puzzle. So today, we're diving deep into one of the most basic questions a kid can ask. And I promise you, by the end of this video, you're going to see the sky completely differently. Before we get started, check out the link in the description to download our ebook. Let's get into it. Think about it for a second. The sun emits white light, right? That's what we see when we look at the sun itself, assuming we're not frying our retinas. White light is actually a combination of all the colors of the rainbow mixed together. So if the sun is sending us white light, why isn't the sky just, I don't know, white or clear? Why blue specifically? And here's another thing that'll blow your mind. The sky isn't always blue. At sunset, it turns orange and red and pink. On the moon, where there's no atmosphere, the sky is pitch black, even during the day. So clearly, something is happening in our atmosphere that creates this blue color. But what? For most of human history, people didn't have a clue. Ancient Greeks thought the sky was a solid dome. Some cultures believed it was the home of the gods. Even brilliant minds struggled with this question for centuries. Enter a guy named John William Strutt, better known as Lord Rayleigh. In the 1870s, this British physicist was trying to figure out why the sky was blue, and he discovered something incredible. He found that when light travels through air, it doesn't just go straight through like a laser beam. It actually interacts with the molecules in the atmosphere. And this is where things get really interesting. You see, white light from the sun is made up of different wavelengths. Red light has long, lazy wavelengths. Blue light has short, tight wavelengths that are almost frantic in comparison. Now, when sunlight hits the molecules in our atmosphere, nitrogen and oxygen mostly, something called scattering happens. Here's the key. Shorter wavelengths get scattered way more than longer wavelengths. It's like throwing different-sized balls at a chain-link fence. A basketball might bounce off or slip through without much trouble, but a ping-pong ball, that thing's going to ricochet all over the place. Blue light, with its short wavelength, is the ping-pong ball. It gets scattered in every direction as it crashes into air molecules. This is called Rayleigh scattering, named after our friend, Lord Rayleigh. And this scattering is why when you look up at the sky from any direction, you see blue. That blue light has been bounced around so much that it's coming at you from everywhere. But wait, you might be thinking, if blue light scatters the most, what about violet? Because violet actually has an even shorter wavelength than blue. Shouldn't the sky be violet? And you know what? You're absolutely right to ask that. The sky actually does scatter violet light, even more than blue light. So technically, there should be a fair amount of violet up there. But here's where human biology enters the chat. Our eyes have 3 types of color receptors: red, green, and blue. We don't have a dedicated violet receptor. When violet light hits our eyes, our blue receptors respond, but not as strongly as they do to pure blue. Plus, and this is crucial, the sun actually emits less violet light to begin with compared to blue. And on top of that, violet light gets absorbed more by the upper atmosphere before it even reaches us. So when you combine the physics of light scattering with the biology of human vision and the composition of sunlight, blue wins out. It's like a perfect storm of factors that gives us that gorgeous blue sky. Now here's something they definitely didn't teach you in school. The sky isn't actually blue everywhere you look, at least not the same shade of blue. If you look straight up on a clear day, the sky is a deeper, darker blue. But if you look toward the horizon, it's much paler, almost white sometimes. It's all about the amount of atmosphere the light has to travel through. When you look straight up, sunlight takes the shortest path through the atmosphere to reach your eyes. But when you look at the horizon, light has to travel through way more air at a shallow angle. More air means more scattering, and here's the twist. When light gets scattered multiple times, all the colors start to mix together again, which makes the light appear whiter. That's why the horizon looks washed out. And here's another mindbender. The sky on Mars is actually red or butterscotch colored during the day and blue at sunset. Complete opposite of Earth. This is because Mars has a thin atmosphere full of iron oxide dust, basically rust particles, And these larger particles scatter light differently than our air molecules do. The physics is similar, but the particles are bigger, so longer wavelengths, like red, get scattered instead. Wild, right? Okay, so if blue light scatters everywhere during the day, why do we get those incredible red and orange sunsets? This is probably my favorite part. When the sun is low on the horizon at sunrise or sunset, its light has to travel through a much thicker slice of atmosphere to reach you. Imagine the light is taking the long way around the edge of the Earth, instead of coming straight down from above. As sunlight passes through all that extra air, the blue light gets scattered so much that it basically scatters completely away from your line of sight. What's left? The red and orange wavelengths. These longer wavelengths don't scatter as easily, so they punch through all that atmosphere and hit your eyes directly. That's why the sun itself looks orange or red, and why the sky around it lights up in those warm colors. You're literally seeing the light that survived the journey. And pollution and particles in the air can actually make sunsets more vivid because they add even more stuff for light to scatter off of. So, in a weird way, some of the most beautiful sunsets happen in places with more atmospheric particles. Nature's silver lining, I guess. Here's something fascinating from a historical perspective. Before we understood Rayleigh scattering, the color of the sky was a genuine scientific mystery that puzzled some of the greatest minds. Leonardo da Vinci thought the sky was blue because of water vapor. Isaac Newton had theories about it. Even Goethe, the famous writer, spent years developing color theories to explain it. And different cultures described the sky differently throughout history. Ancient Greek texts rarely mention a blue sky. Some scholars think ancient peoples might have perceived colors differently, or at least categorized them differently than we do today. The linguistic history of color is wild, and blue is often one of the last color words to develop in languages. Makes you wonder how much of what we see is filtered through culture and language. Understanding why the sky is blue isn't just a fun fact for trivia night. This same principle of Rayleigh scattering explains why smoke from a fire looks blue when seen against a dark background. It's why distant mountains look blue or purple. It's even used in medical imaging and astronomy. Astronomers use this knowledge to filter out scattered light and get clearer images of space. And understanding light scattering helps us study other planets' atmospheres. When we look at exoplanets, planets outside our solar system, we can analyze the light passing through their atmospheres and figure out what gases are present. We're literally using the same science that explains our blue sky to search for signs of life on other worlds. So here's what I want you to take away from this. The next time you look up at the sky, remember that you're not just seeing blue, because that's the way it is. You're witnessing a cosmic dance between light and matter. You're seeing photons that traveled 93 million miles from the sun, only to get bounced around by molecules so small you'd need trillions of them to fill a sugar cube. That blue isn't a property of the sky itself. It's an interaction, a conversation between light and air and your own eyes. The sky is blue because of quantum mechanics, because of the size of molecules, because of the wavelength of light, and because of the specific way your brain interprets signals from your retinas. And that's what's so incredible about science. The most ordinary, everyday things we take completely for granted are actually deeply strange and beautiful when you dig into them. Every time you've ever looked up, you've been seeing evidence of the fundamental forces of nature at work. So yeah, the sky is blue, but now you know it's blue for reasons that connect physics, chemistry, biology, and even a little bit of history and culture. And that's way cooler than anything they taught you in school. If this video made you see the world a little differently, that's exactly the point. Stay curious, keep asking questions, and I'll see you in the next one.